Does anyone see slides on the screen? Worried me there for a second. All right, Brandon Rhodes. I am very happy to be here in Cardiff. This is my very first Pycon UK ever, and chose as my topic for this morning Python and the glories of the UNIX tradition. When I was a small child, one of my dad's best friends, good friends of our family, was one of his coworkers. Sometimes on the weekend, your family would go visit theirs. The adults would stay up talking late, and they had to do something with me. The other kids were playing, and they found that if they wanted to get me really quiet, they could take me upstairs, and in the little office upstairs, it was like a television screen, but with letters on it. It was a dumb terminal hooked up to a modem, and that made all these noises, and they'd connect the phone to it, and up in green text on this black background would come a computer prompt from which Dad taught me to launch a game called simply Adventure. Also known as the Colossal Caves adventure game. It was the very first computer game ever that let you explore a world inside of the computer. Previous games has been like chess or checkers, purely abstract. This one, you got to walk around and eventually find your way into a cave system. It was sort of simulated inside of the computer. You were supposed to try to find treasures and gold, but there was danger as well. If your lamp ran out of power, you could fall into a chasm in the dark and die. The game would exit, and you would have to start over again from the beginning. There was no way to save your game. The challenge was to see how far you could get this time without being killed. And I hope I won't, not too much of a spoiler, to just say that once you got past the simple stuff like your light going out, you tended to start fairly regularly being killed by characters with axes. I was 7 years old. This was kind of disturbing stuff. And I would get to where it was a very slow terminal. You could see it type each line across the screen, waiting to see if you lived or not, having moved west into the Hall of Mists or whatever. And so I would get to where after a few games and a few deaths, did I mention, at the hands of axes, I would be ready for a rest. And so my father taught me about something that to me became another adventure. He showed me that on this Bell Telephone Laboratories computer system that we were logged into, that there was another kind of adventure I could have if I learned a few commands, one of which showed me where I was, one of which it was like the look command in an adventure game. I could look around and see the names of the directories or files around me, and I could move in and out of those directories. So when the adventure game became a little too intense, I was tired of being constantly on edge and trying not to die, I could instead go explore a file system. Some areas were very deep, some were very shallow. I'd play a game to see how deep a part of the file system I could get into before it bottomed out and there were no more folders. Some were off limits to me. I would try to CD into them and it wouldn't let me. Never set off any alarms and no one ever came running, so I would go in another direction and keep exploring. I learned later that I was exploring something called the UNIX System, one of the UNIX systems at the Merrimack Valley location of Bell Laboratories, and I didn't know it then. It was in fact extremely non-obvious then, but I was preparing myself pretty well for the 21st century, and I had no idea. And the language that I now love and practice as my profession, Python, is a part of that tradition of languages and tools that grew up at Bell Telephone Laboratories around the UNIX system. And so for my topic this morning, I wanted to share some about the links and the commonalities between that very early set of ideas I was exposed to and what I do today. What does Python and that tradition share in common. Two quick terms: the operating system on your computer is the one little program that you trust with all of the hardware. It used to be computers ran one program at a time. That program did whatever it wanted. But once two people wanted to use a computer at the same time, there had to be a way for them to share the printers, share the disk drives, without overwriting what each other were doing and without seeing each other's passwords and so forth. So we gave control of the hardware to a special program called the operating system, and we walled off each running process into an area of memory that it owned and that was the only memory that it could touch. Well, if the OS has operating system has walled you off, how can you talk to the printer? How can you print to the screen? How can you read from the keyboard? The answer is a system call. I'll be using that term a lot. The system calls are the basic subroutines you can call that ask the operating system to do something for you, and it can either say, no, I'm not going to let you look at that. That's off limits. That would let you see someone else's password or whatever. Or the operating system can grant the system call and return the disk block you want to read or the characters from the terminal that you want to see. Those will be two fundamental concepts as we go forward. So, what have I found survived from that early tradition I was exposed to that has made it all the way into the Python language that we use today? First, the practice when writing a system of going ahead and implementing something and then iterating quickly. Unix was born out of the ashes of a large operating system called Multics. It was going to be the greatest of all operating systems. Thousands of pages of documentation were written as they tried to get an idea of what it would do. And at the 4-year point, Bell Telephone Laboratories determined that maybe Multics was going to be wonderful, but it wasn't going to be delivered soon in a usable form for the laboratories. So they canceled their involvement in the project, and a few of the refugees from that within Bell Labs, who kind of really liked some of the ideas and wanted to try them out, surreptitiously got a computer and started to work on their own tiny operating system that would carry some of the good ideas forward. Multics was the big one, so they decided to call their small one UNIX. Interestingly enough, this is become this approach, build something, throw it away, and then build the one you actually wanted, is a recurrent theme in computing history and a famous experience. It wasn't what the Multics people were intending. They didn't write all those thousands of documents to throw them away, but it wound up being the second try at those ideas that wound up surviving. I recommend, it is now, I just found while preparing this talk, archive.org now has online the famous 1978 issue of the Bell System Technical Journal, which normally was a technical journal about electrical engineering and telephone signals and microwave signaling and satellites, that dedicated an issue to their new UNIX time-sharing system. Again, to them, the big feature of an operating system is it lets several people share the CPU time on a single computer instead of everyone having one of their own. I recommend reading through it if you want to understand why the tools we have today operate the way they do. But it will describe that journey from Multics, big, complicated, never finished, to something smaller and simpler that's very remarkably similar to Python's story. Guido van Rossum got to be part of the team that implemented the ABC language, large, heavily specified, and so far as I can tell, never used. Guido took those ideas and started his own project that tried to get them in front of real programmers quickly to see how they would do. So, first idea, implement something quickly, implement something small, and start trying it out on real users. Fortunately, in this case, the users were developers. Developers don't do as well when the users are like someone else you have to go talk to, but we're pretty good when we're our own users. Next feature that those early systems had was interactivity, and this wasn't an easy thing back then. You were on a teletype kind of typewriter that the computer could use to type back at you. And because typewriters can't make characters disappear, you just had to keep typing even when you made a mistake. So the backspace character or the kill line character was just something they chose off of your keyboard that you hopefully wouldn't want to type very often, that you used to tell it to ignore a certain number of characters you had just typed. So interactivity was not an easy thing. It required awkward conventions, but they thought it was so valuable, they went ahead and typed little backspace characters and counted to make sure that they had typed them correctly, because there was so much value in this idea of being able to type and immediately see a result, instead of having to wait and be slowed down in your exploration. And it wasn't just in the UNIX shell. The program they wrote on UNIX that accepts your commands and runs them was not just interactive, it was a whole programming language. There are operating systems with very disappointing shells. All you can do is type the name of an application and see it launch. But if you've ever done this on your Linux machine or Unix server or MacBook, you know that not only can you run a command like SSH, you're inside of a programming language that has loops, if statements, and you can automate tasks using the fact that you're sitting at a program language prompt. Both Unix and Python, of course, I hope you've worked at its prompt before, worked to offer a full programming experience interactively and saw value in the ability to make it fast to sit and experiment and iterate. This is what it often looks like at the shell. Maybe I want to get a sorted list of the usernames on my system, so I peek at the password file, look at its structure, experiment till I've figured out how to trim off everything past the first colon, and then can pipe that into sort to get out, starting with, I would have thought A, but apparently my laptop has an underscore in one of the usernames. Learned this week. I can iterate, put together one step at a time, a solution that answers a sophisticated question. Here's the same question as you might iterate on it at the Python prompt. Open the password file and read the lines, get one of them, look at it, figure out how to split it into pieces, take the first one. That's a username. Take all of them, you've sorted all of the usernames. Iteration lets us get small steps towards a solution rather than having to somehow write it all at once. So interactivity was a value of that early UNIX system that's been carried forward to today. Recursive data layout. UNIX, all operating systems have to answer the question, how should a disk drive maintain its list of files? Where do you put the list of all the files on the disk? Who can look at the list? How long, as it gets longer, how should it be organized? Should you, early disk drives, you just had a list of files. I mean, you could fit like 5 of them, right? So you just kept them in a list. But as disk drives started to have hundreds of kilobytes of storage, you started having dozens of files, maybe 5 dozen files. Well, how are you going to keep track of the fact that I'm putting files on there and you're putting files on there? Maybe you need a directory of files for each user, but then there are some shared files that need to be in a list maybe that the system owns. And then what if I want to copy a file so another user can use it? I might use something like a Dropbox directory that's just for transferring files. Different early operating systems had different ideas about how many lists of files there should be on the disk drive and what the API would be for getting the operating system to give you, you can't read from disk yourself, each of those lists. Multics had this crazy idea. What if every directory, every list of files was itself a file? It's like the movie Inception, but on your disk drive. And this blew the doors open, this idea that, well, what if a list of files is itself a file? This is called a hierarchical file system. All of a sudden, the naming problem, well, how many of them are we going to have and how do you discover how many there are, is solved. Because directories are now just files on the file system that, like other files, have names you can use to get to them. How do you read their contents in early Unix? You simply open and read the contents like you do with any other kind of file. They had a special format, but if you understood it, you could read the directory entries. And they decreed that it was allowed to nest a directory inside other directories. This means that you could give each user their own directory, and if I started creating so many files that I wanted to split them into separate lists, I didn't have to go to the sysadmin and ask for a new directory to please be allocated for me on the drive. I could just create a subdirectory of my own directory I had been given and go to town creating as many subfolders as I wanted. That design, which was invented in Multics, carried forward into Unix in a much more elegant way, became the standard. It's how all file systems essentially are now designed. What does Python have that I would say is the equivalent? The fact that Python absolutely nailed the concept of recursive data structures. Again, recursive is a fancy word that just means that something can have an identical such thing inside of itself. Python data structures, and this was revolutionary for the time, especially for scripting languages, can nest inside of each other arbitrarily. There's one exception we all learn, which is that a list of things can't be a dictionary key because it could change and be orphaned inside the dictionary data structure. Only tuples can be a sequence that's a dictionary key. But with that one caveat, otherwise we can just go to town, putting data structures inside of data structures, inside of other data structures. I've seen a programmer, slightly crazy, but put a dictionary inside of a dictionary inside of a third dictionary. It was not necessarily easy to use, but it got their data organized in the way they needed, and they needed to know no special rules, no special syntax, no special limitations to get it done. If you've used other languages, other scripting languages especially, you know that that's normally impossible, normally against the rules, or normally very awkward. I'm looking at you, Perl. If you want to put data structures inside of each other. But that ability to use a little list or tuple to organize data and then to put it in a surrounding data structure is really what sold me, one of the things that instantly sold me on Python. I had never been able to build more general, complicated data structures out of simple ones with such a clean and elegant syntax that let me move so quickly. So I would say that as a strong inheritance of Python is having a recursive, completely general data layout. I should mention, by the way, when I say inheritance, I mean many removes. I don't mean that Guido, when he came out with Python in 1990 and released it in 1991, I don't mean that he looked at an operating system and tried to make a language that was like it. What I mean is that this whole tradition of tools that I'm talking about today, that started in Bell Labs in 1970, has certain patterns that come up again and again, and had already come up several times in the history leading up to Python. What I mean is that Guido was at work in a community and in a practice that had internalized these successful properties of that first UNIX system. Another very, very important property was the use everywhere that Unix could of plain text. What's a plain text file? Originally, it meant a file that consisted of the printable ASCII characters, including space, and that was, rather than just being a huge string of characters, split into smaller ones by use of the new line character that we type in Python as \n. Unix tends to use plain text for everything that it possibly can. File names? Some operating systems file names, there's special rules, they have to be 8 characters and then a 3-character extension, and you can't have 2 extensions and you can't have 0 extensions. There have been operating systems with a lot of rigid rules about file names. Unix, it's a plain string, means nothing to the operating system. It's a label that you can make as interesting as you want with no limits on what you put there, which allows a lot of interesting possibilities beyond the operating systems that let you only have 1 dot back in the old days. And it was Unix that showed the way forward for this modern practice. What about a path, where you're telling the system not just a file name, but where it's found? It's just plain text. Craziness. Operating system experts at the time frowned, and they said, you can't do that. Every time you ask to open a file, the operating system is going to have to look through the string to find the slashes, and it's going to have to pull each of the pieces out. You should have to pre-process that and turn it into a special data structure for the OS, or your system will run slower. And the people inventing Unix said, yeah. But it'll be easier to use. And this is a recurrent practice in Unix and in Python, taking a few % hit, going a little slower in order to do something that's just fundamentally simpler. So paths, the fact that they're just a string, meant that instead of every single command you write, every program you write, having to understand that it has to split it by slashes and hand each piece separately to the OS, the fact that all your programs were just handing this entire string to the operating system to name a file meant, one, that you didn't have to worry that one of your commands was going to be miswritten and handle paths a little differently than the others, but it meant that all programs had to do was get what you typed as the path and hand it to the OS and not even think about what it meant, similar to the way that URLs today can carry all sorts of information, and as long as browsers and tools take the URL and then send it on to the part of the library that makes the call, all of that information makes it through intact in a round trip. All right, we now get to something very serious. What about the password file? Password files, you're supposed to have usernames that are each unique. You need to be able to look up a username very quickly. Obviously what we need is a tree or hash table laid out on disk that lets you uniquely store usernames once along with a record about that user. Unix looked at that and said, no, we're not going to do fixed length records. We're going to do an on-disk hash table? No. Let's have a plain text file. And the operating people said, that's craziness. That means that every time someone tries to log in, the operating system's going to have to start at the first line. It's going to have to find the new line character, and it's going to have to look at the beginning of the next line and find the colon, pull out the username, and compare it to the user that's trying to log in. It's then going to have to go to the second line and the third line, all the way down until it finds the user that's trying to log in. This is going to be madness. Your system is going to run more slowly because you're parsing a text file all over again that you could have already parsed every time someone logs in. And the people writing Unix said, yeah. But if your password file is plain text, you can search it with grep. You can sort it with sort. You can pull pieces out of it with sed, as you saw me do a minute ago. If it's plain text, you don't have to write a special program to sort the list of usernames or a special program to collate information from it. If we eat that bit of expense of making it plain text, then all of our normal tools will work on its data the same as they work on one of your normal plain text files' data. Really, the Unix operating system was a vast act of divestiture. Operating systems were supposed to do dozens of things. The inventors of Unix said, yeah, let's have an operating system do maybe 3. Maintain a file system, maintain a process list, manage the physical I/O devices, a few other things. But basically, Unix was an act of looking at Multics and saying, yeah, it would be great to write 20 system calls for maintaining a specialized, high-efficiency password database. But let's just not. Because you won't finish writing your operating system, for one thing, and second, you will have created something that you can't use your normal tools against. Unix was a vast act of deciding to get operating systems out of the business of things like passwords. You have a login program that knows how to read the password file. You have a password setting program that knows how to read it. But the operating system literally does not know it's there. That was a very powerful concept which changed the way operating systems were written. Plain text means that standard tools, text processing tools, can operate on system data. What about your personal preferences? You know, we have a time zone that you might prefer things to be displayed in, a language that you want error messages in. Some operating systems would have a special registry. Some operating systems would have a bunch of special calls to manipulate it. In Unix, it's simply plain text. It's a list of strings called the environment passed to every program you run, and literally they have to go parse the equal signs out of every entry if they're looking for your time zone, if they're looking for your preferred language. It's slower, yeah, but it's much, much, much simpler. What is the equivalent in Python? For me, it's the fact that Python uses and reuses the same plain data structures, the tuple, the list, and the dictionary. Three of my favorite examples are, what about the arguments that you're given at the command line? The operating system delivers them as null, a null-terminated packed array of strings with a double null at the end. So obviously there should be a special way that we manipulate this in Python, maybe some special calls we use. Nope. It's just sys.argv, your command line arguments are a normal list. What about the path that we import from? It's a list of strings. Okay, very low level. What about the modules that we've imported and that are in RAM? You would think that would be a special data structure. It's just a simple Python dictionary. Python, over and over again, like the UNIX system did with its operating system level knowledge, again and again chose to represent it as the simple data structures we use for our own data and that we therefore already know the rules of and know how to manipulate. Unix introduced us to the idea of plain text. The corresponding idea in a language is plain data. Another powerful concept from the UNIX system. Everything is a file. That's almost a motto of the UNIX system. What does it mean? With a regular file, we quickly learn, the Python file-like object, a set of maneuvers we can do to get data in and out and to move back and forth. I already mentioned that directories in Unix are also files that at least traditionally would also be susceptible to the same three operations if you want to. You weren't allowed to write to a directory yourself because you could corrupt the disk and make the file system unusable, but you were allowed to read just like from a normal file. Well, what about binary applications like binls or the C library? In some operating systems, they were delimited and stored specially in a special area. Not on Unix, completely normal files that you can set up, modify, and upgrade using the perfectly normal file operations you use for everything else. Now, you're going to ask, but how then can the operating system know it's executable? If the OS is really divesting itself of metadata, of having a content type, or making you set an extension, how does it know which files are executable and or what executable format they're in? The answer that Unix adopted is the idea of magic numbers. The first few bytes of each file are a special code that you can look at, the operating system can look at, to know what kind of file it is. There's a command called file on your OS X machine, your Mac, or your Linux laptop, and you can try it out on different files. It will look at the header to see if it can find any special binary bytes, and if it does, it'll look them up in a table and tell you, just like the operating system looks to see, what kind of file it is. All right, what about I/O? Computers hooked up to terminals, characters come and go. It's hooked up to printers, characters come and go. In Unix, those are just completely normal files under a special directory called dev, but they're not normal files. I mean, they're completely fake files. They're not really files on the disk, but they act like files, and read and write will get data from a printer exactly the same way as it will pull it from a file. File permissions, therefore, are the way that Unix secures its TTY and block devices. So you get like this freebie because everything, all of your I/O devices are files. All the normal rules for file access apply. And when I log into this machine, it gets the TTY I'm logged in as, temporarily sets me as its owner, and sets up the read and write bits so that other people can't see my password when I type. We get to reuse all of those practices and knowledge in the domain of devices. All right, really low-level operation here. What about a file system checker that wants to read the file system and repair it? Does it need a dozen special system calls to support the maneuvers it needs to do? No, because the list of currently mounted file systems is is a special file called proc mounts. You read it, and it tells you what devices on your system are currently mounted as file systems. And then there is a block file that lets you get into each partition on the drive as though it's just a big playground, as though it's just a big file that you can seek back and forth and read and write from. This means that as low-level an operation as checking and verifying and repairing a file system can be done through the same bog-standard operating system calls that you use for reading and writing a little text file. In Unix, everything is a file. Python chose a similar symmetry when it made everything an object. You're already hopefully familiar with this, or soon will be, that there are a few object protocols built into Python, built into its syntax, that you're going to find work the same way over and over and over again with all kinds of different data structures. Everything is an object is what powers Python's idea of duck typing, that I can pass you all kinds of objects, and as long as they behave in the ways you expect, you're able to use that object. That's the equivalent in Python of the old Unix idea that if you write a program that can read its input, I could hook you up to a printer, I can hook you up to a terminal, I could hook you up to a raw disk image, or a plain text file, at my option, because as long as you're just opening and reading, I can hand you and connect you to whatever I want. So in Unix, everything was a file. Python riffed on that idea when it decided that everything would be an object. First-class errors are, to me, a very important part of programming. The fact that you can see errors and ask about them rather than having to, run a program and without knowing whether it succeeded or failed, go back and look at its output to try to, see if the word error got printed as it ran or something. In Unix, every program that exits has to issue an integer status of whether it succeeded or experienced some kind of failure. You can, with the shell, if you ever want to play with this, $? will show you that code. That's sometimes used in things like while loops and if statements. The way that they're defined in Unix, they choose the if part of it if the command succeeds, and the else part if the command fails. Now, you might actually have been believing, if you've only used the shell a little bit, I backed up a slide or two here, I realize you might have been believing that errors are just ignored in Unix because you're always put back at the prompt. Whether the command you ran succeeds or fails, you're dumped back at the prompt. If you've ever tried writing a simple shell script, it just runs top to bottom, ignoring any errors, and keeps going. Anyone had a shell script that you forgot it would just keep running if one of those commands hit an error? The front row. The reason is because the bash shell, when you run it on a script, unless you tell it otherwise, wants to act just like the command line, which does survive errors and keep going. If you want to have bash act more like a programming language, you can run your script with -e, or once your script has started, if you don't trust the person who runs it to remember, you can set -e inside the script. That's a flag that makes bash act more like a programming language and will stop when the grep, the command, whatever you ran, exits with an error, because Unix does know the difference. And also, even though if you've just run simple commands a few times at the prompt, you might have the idea that error messages and the real output that you're waiting for are all kind of grouped and mashed together because it sort of all comes out on the terminal together. That's not actually what's happening under the covers. Unix is very careful. Error messages go one place, data goes another, so that you don't munge up the valid data that's being output with on-the-side error messages about missing files or directories. If you use redirection, and that's a subject for another talk, you can actually peel out those two separate data streams and see that your data is intact, even if some error messages had to be issued along the way. That's Unix's way of keeping errors clean. Python's approach is first-class exceptions, which in a computer language does very much the same thing. When you do something that dies with an error, the program tries to exit there and starts, it interrupts the function that's running, which stops running, and it looks outward for whether you've set up any handlers for that error. That means that you don't, as in some languages today, like the Go language from Google, you don't, every time you run open, have to stop and check an error code and compare it to 0 or 1 to see if it succeeded or failed. There are languages where every line you write is followed by a check of whether that previous line succeeded or failed. You don't have to do that in Python because exceptions will simply stop the program at a failure because Python internally is running that little if statement. Well, did it succeed? If not, let's bail out. Did that next line succeed? If not, it bails out. That pattern is built into Python, and because the exception that's raised is itself an object, the data that tells us what happened can just be attached as normal attributes. So Python has a separate channel for carrying data about errors, just like Unix does. Both of them support first-class errors that can be recognized uniformly by all tools and that can carry special data. Pipes, which I don't have time to go into in detail, are a favorite feature of Unix. Multics had something similar, but it was Unix that developed a syntax that made it easy and then built a whole ecosystem around it. The equivalent in Python, of course, is our iterator protocol. The fact that it came about, I believe, in the early 2000s. It was not an original feature of the language, but since then has let us write more and more and more tools in Python that, just like primitive tools in Unix can be strung together, let us put together looping operations in Python so that they feed from each other's data. Another lesson, I think, from the early years of Unix is go ahead and offer power tools. There were some old sayings going around in the 70s, like use simple algorithms as well as simple data structures. Python's answer to that is no, let's not. Let's use complicated data structures. Python just invites you to use the set and the dictionary. If you've ever watched a talk about how the dictionary works under the hood, it is not simple, it is not easy to get right. It has taken years and years and years of honing to make it as efficient and wonderful as it is. But the Python philosophy is to get a few power tools, drive them nearly to the point of perfection, and then make them simple for you to use. The equivalent that I'll cite in the Unix tradition is sort. Did you know that sort can sort input streams larger than RAM? It's actually kind of rare. A lot of sorting solutions fall over the moment that your collection is bigger than the memory on your computer. Not sort. It's essentially it's a map-reduce system. If it's reading in the input it's supposed to sort and it's about to fill memory, it'll start paging it out to temporary files it creates in the temp directory so it has room to read in even more. And then when the input finally stops, it will merge back together all those temporary files. That's something that is difficult to write, difficult to get correct, took a lot of work, and then it's just delivered to you. A first-class solution like the Python dictionary that's not going to break, that's not going to fall over on you, that's always going to work. It's a power tool. And in both of these traditions, we tend to, instead of asking you to use very simple tools, we give you some very powerful tools that we try to write so that you can use them repeatedly. Sort in Unix, the dictionary is my favorite one in Python. Point I'll just make quickly, both of them went with a very simple core. with then a lot of tooling around it, Unix was easy to port. One of the first operating systems that was portable because the kernel was fairly small, and once you had that, you could just recompile all of the other tools to call open and close and read and write. And they just worked on the new system because they couldn't see the hardware, they could only see those abstractions. Python, because so much of the standard library is written in Python, all you have to do is in another environment, if you want to re-implement Python, is to re-implement the core language that's written in C, and then all of the standard library should just work for free because it's written in Python. And I can't resist celebrating the fact, I know this isn't a really big deal and it's not original to Unix at all, but I love the fact that Unix does reference counting. It's what Python does to know when it can deallocate things. You might not have tried this before, but when you do an ls-l on a file on your MacBook or your Linux laptop, it has a little count of how many names there are for a file. You can have more than one. Here I create a second name for a little file, so its reference count goes to 2. Both of those names now have to be removed before it would be safe for the operating system to remove a file. So question, when the final link to a file disappears, and its reference count is 0, can it be removed? Not necessarily, because a process might still have the file open. Now, weak operating systems, of course, just forbid the removal of open files, but that's not what Unix did. What Unix did is when you open a file, the inode is copied into memory for easy reference. And there, the link count is the sum of the number of names on disk pointing to the file, plus the number of processes that have the file open and are reading and writing and using it. This means that if I remove both names for that file, all right, now the link count has dropped to 1 on disk and 3 in RAM, remove the other name, I'm down to 0, but it's not disappeared from the disk yet, because 2 processes are still using it. Should the operating system crash and reboot, the disk repair tool will note that the inode has a 0 reference count and remove it in the file's contents, but unless the operating system crashes, the file's going to stay there for me to use. You can do this right in Python by creating a file, unlinking it, removing it from the system, and you'll still find you can read and write from it. If you do a LSOF of that Python process, you'll see the file is open, is available, has a length, has content, and is deleted. Doesn't exist on the file system anymore. This is a way that you can create a buffer of data that you can grow and shrink and read or write from that has no way for other processes to get to it on the file system, and that will be automatically removed when your process dies. You don't have to have an @exit handler that tries to clean it up. If you look at the number of links by statting it, you'll get 0. Python has this built in today. The temporary file, it's up at the top these days of the documentation for the temp file module, does exactly this. Creates a temporary file and opens it, removes the name, and hands it to you. You now have a file that however violently your process crashes will be cleaned up because it was its last user in the operating system. This is how an installer on Mac or Linux can remove an executable. Like, the other day I said, apt upgrade Google Chrome, and it upgraded, even though I still had it running. It didn't tell me I had to exit it, didn't tell me I had to stop my work while everything upgraded, because it can simply remove Google Chrome from my drive, which is okay because the file will still exist because my Google Chrome process is keeping it alive, is holding it open. And then replace it, write a new one in its place without the old copy of the process having to exit. This is really great on web servers where downtime is a bad thing, because instead of having to take a having to stop a program so that you can remove it and replace it and then bring it back up, you can instead just keep it running, remove the executable out from under it, rewrite it, make sure everything looks good, then turn it off and back on again. So it is a favorite feature of mine that the Unix file system does reference counting, just like Python does in memory to know when to free strings and things like that. My final point is that with Unix, was a first magnificent example of sharing the code. Bell Telephone Laboratories were part of the Bell system that in 1958, they were sued and it was pointed out they were a monopoly. The government let them run the phone system. So they were forbidden, because that was kind of an advantage to have monopoly rights over the phone system. They weren't allowed to go into other industries and start trying to quash other private companies by competing with them. This meant they couldn't get into the operating system business. When Unix was invented, when it started to be used all back and forth across Bell Labs, they couldn't commercialize it, so they set up a little licensing fee, and universities, for I think $200, could get a license, which meant they were sent a tape with the whole source code of the operating system to use. So Berkeley and a number of other computer science schools immediately bought copies because they could now teach operating system classes with a real working research operating system as the thing that the students worked with. That created a whole group of people at Berkeley that created a Berkeley Standard Distribution, BSD of Unix, which became the ancestor of the Next Machines version of Unix, which became the ancestor of OS X that runs on every Mac in this room. Because it was available, because you could get the source code, a whole tradition sprung up. It also inspired Minix, dotted line, because no source code was transferred, but the design of Unix inspired another operating system, Minix, which inspired Linux. You know, I can't believe it. I used to be a little boy sitting upstairs while the adults talked downstairs, typing LS and PWD into a glowing green terminal. Today, I work at Dropbox. Every one of our servers runs a version of Unix. Every one of our laptops there runs a version of Unix. And unexpectedly, after 2 terrible decades when everyone else was using Windows, I'm like, we won. And just as Unix pioneered that direction, creating freedom around source code, which led to a whole tradition. It wasn't a product that you bought in an adversarial relationship. It was a tradition that you entered and something you learned that created community. My dad told me that you learned Unix from the other people at the lab. They'd look over your shoulder and say, wait, you're not going to write that in C, are you? Let me show you awk. They learned it as a community, just as we have come here today, just as we've come to Cardiff, to learn from each other, look over each other's shoulders, and learn. Welcome to the community. Welcome to PyCon UK 2016. Thank you very much.